So welcome to this session. We are here to talk about our work on serverless programming. So the idea here is that serverless programming is a big thing. And so far, it's been kind of held back a bit because, while it's very easy to create stateless function, it has not been so easy to create entire stateless applications. And so what we're looking at is really how to make that work better for programmers, improve the experience for writing entire serverless applications that go beyond just small functions. And we're going to have a bit of a tag team here. So we're all talking a little bit. We have Konstantinos, who is my intern right now. He's going to start. We have David, who is working at Durable Functions at Microsoft. He's going to take over a little bit later. I'm also going to have a piece of the talk. And I see Christopher is also here. He was interning with me last year and the year before. So a bit of his work is also in here. And at this point, I guess I'm going to hand this over to Konstantinos, who is going to have the first segment. So let me see. I go over here. Okay, this one. Okay. So Konstantinos is the host now. And if I look like I'm rudely not looking at you, it's because I'm looking at my other screen, but it's still the same meeting.
So can you see my screen, everyone?
Yes.
Okay, cool. So yeah, hi everyone, I'm Konstantinos. And yeah, I will start this presentation by talking about cloud applications and the issues that exist. Start with the issues that exist when developers have to implement and deploy a cloud application. So a lot of these issues are related to management questions. So a developer has to figure out how many resources to allocate. If they allocate too few, then the application will not be able to handle the load. If they allocate too many, then they will pay unnecessarily to the cloud providers. They have to solve issues related to reliable execution in the presence of failures, which are pretty often in distributed environment. They have to be able to adapt to load increase. So if there's increased load, they have to spawn more VMs, or if, in the case that there is inactivity, they might need to stop some VMs and then restart them later when there is an increase in load. And also there is the issue of monitoring the application state and knowing if everything is going okay and exactly what state the application is in at any point in time. So traditionally, we think about an axis of control and productivity where developers have to pick between different programming languages when they develop their application. Some of them allow for finer grained control, but require a lot of effort, while others require no effort at all, and but require but give you far less control. And this analogy works in the cloud too, where the more we go towards the left, the more of the issues that I mentioned at the beginning developers have to face and address. To address those, serverless is a solution and a model that allows developers, gives them less control, but allows for more productivity. And a lot of cloud providers actually support them already, like AWS and Microsoft. And to convince you that people believe that these are pretty useful, this is a cloud report that shows that serverless in 2019 was the top growing service, even more than machine learning. Yeah, so what exactly is serverless? So as Sebastian said, the high level definition is that serverless applications essentially do not see the notion of a server under them. So they're agnostic to any server. So more precisely, the main concept is serverless functions, which are essentially stateless with an asterisk, which we will come to in a little bit. Functions that take some input and return some output. So these functions are very easy to deploy and scale, as they can be invoked, more of them can be invoked in parallel if there is an increase in input. And the cost is per invocation. Also, they can be written in any language, since the way they communicate with the external world is through REST interfaces. So to come back to this asterisk, serverless functions are not exactly pure in the traditional sense, because they can call external services, which are either key value stores or queues or databases, which essentially make up the standard library of cloud programming. So as you can see here on the right, this function deletes all files in the storage, or this one reads the value of a counter, increments it, and then saves it back. So together with functions, serverless also contains storage, either in the form of key value stores or tables or blob storage, and also transport, such as queues that allow for communication between these different serverless functions. So serverless is already very useful today and great, but there are several issues related to state management and synchronization. So first of all, functions can interleave and erase arbitrarily, and synchronizing them has to be done through storage, which is extremely challenging, especially if you're not a distributed systems developer. And also, hosts can fail in the middle of execution, where functions have executed part of their code, having done some external calls, but not all of them, leaving behind inconsistent state that has to be cleared up by the developer somehow. And finally, there are also costs related to there are issues related to cost and performance, since having a function wait for another function to produce its results means that we pay for two functions and not one. And since these functions don't have state, but they use other services and components as their state, such as storage and queues, this means that there is a lot of data movement to and from storage, which wastes a lot of time and in the end also money. So all of these issues can be seen if we look at how a non-trivial application in the cloud ends up looking today. So we have some stateless services which perform computation. Some of them might use some storage service, some key value store, let's say, for their state. And in order to ensure reliability, they persist intermediate results in a queue, persistent queue service that then is read by the next stateless service, and stateless services that need to synchronize right on some storage service. Well, this is far from ideal from where we would like to be, actually. And the proposed solution is abstractions for stateful serverless programming. So we propose two abstraction layers, several frontends in different languages where you can actually write task parallel code standard as you would expect in these languages. And these frontends support stateful workflows and actors with several extensions and restrictions to further facilitate implementing stateful applications in that setting. And on the back end, there is a stateful serverless execution engine, which guarantees reliable distributed execution and is language agnostic. So it can connect to any of these frontends. So with this introduction done, I will hand it over to Sebastian. Somehow. Let's see.
I think I have it. Let me see if I can share the screen. Nope. I'm not host yet.
I think I just made you a host.
Host disabled, participant screen sharing. Let's see.
Do you want? I
have to give it to Sebastian Burkhardt, not the RISE MSFT RISE.
I gave it to the
you
RISE.
Gave it to, okay, I have to pass it on to, yeah, I guess it's my job now here. Yeah. Okay, this should work. Okay. I have a little bit of something happening here that is odd. Can you see my screen?
Yes.
Okay. Okay. So let me fast forward to the correct slide here. Okay, so here we go. All right. So the thing I've been working on for the last several years, and also the Azure Durable Functions team has been working on similar problems, and we have joined forces as of last year, is basically about having these workflows that are very common for business application or all kinds of things, make them easy to express. And it's really about using concepts that are kind of familiar but not available in a serverless context and bringing them to programmers. So the thing we're adding, we already have stateless functions. So there's not much we need to fix there, but we are adding two new things, two new concepts, which are called orchestrations and entities. And this is really to represent workflows and actors. And I'll discuss them kind of separately because they can be understood separately. So I'll start with the orchestrations. So the point here is really to compose stateless functions using the task parallel paradigm. So people have for a long time known that it's convenient to express parallel computations using tasks. But that doesn't mean that if you start writing serverless applications that you can actually write it that way. So traditionally, as Konstantinos said, what you do instead is a rather low-level explicit way of putting together queues and functions and storage. And so what we're going after here is actually writing the orchestrations, the tasks that you want to perform using task parallel code. And the advantage is of course, it's expressive. So the common things that you want to do become very simple to write. And it also has other advantages. For example, the handling of partial executions. So if we understand the way you express your workflow, it means we can recover after failures and resume where you left off. And it also means that we can do better than having functions stay in memory while they're waiting for something to happen. So this is a common issue if you have workflows that run for a long time, such as you're waiting for a user response within a week. And obviously you don't want your function to stay in memory for a week because you would pay for that. And actually it won't even work because functions have timeouts. So if anytime you want to do something that takes a longer time than that, you really need a workflow that is able to, persist its current state in storage. So this is not completely new. So workflows have been around. But what's usually the case is that workflows are they invent programming languages again, using declarative approaches, such as graphical designers or XML-based descriptions. And the thing we really wanted to do here is not invent some special workflow language, but just write your workflow using a normal programming language. And the benefit is that you get all the richness of that language. And I think today this is really what defines, competitive environments for programming, is the richness of the environment, the ability to use all the libraries that come with the language, the ability to call all the things that you want to do in that language. So I think it's sort of the way to go is to take a host language that is rich and extend it to do this. So what does it look like? So let's take an example. So suppose I have a stateless orchestration and I want to do two things. I want to upload a file and then update an index somewhere that stores the name of the file. So on the right here, I have two black boxes. These are the stateless functions, the activities. And I want to do both of these in a sequence. So what I do is I write the thing on the left, which calls those two in sequence. So first I call the first one with add to blob storage. This call returns, hold on a second. Let me do the laser pointer. So this call returns a task. And then here I'm waiting for the completion of this task before calling the second task, and then waiting for the completion of that. And after the second one has completed, my orchestration is complete. So this logically corresponds to a sequential composition of tasks. So you can probably guess the next slide. What if I want to do those two things in parallel? Okay, let's see. So again, I have the same tasks and I have the same entry point, but now what I do is I simply call both of these without waiting for them for the first one before calling the second one, and then I wait for both of them to complete. There's different ways to write this. The syntax here is, it can be exchanged for other ways to writing this. The important part is you're starting to leave the type of thing that is very easy to do with just queues. So imagine for a moment that all you have are stateless functions and queues. So how would you actually implement this waiting for two tasks? It's not so obvious. You can't actually do it with just a queue. So you would need some kind of storage somewhere where you count how many tasks have completed, something like that. But even though this still seems like you could just make, put it together yourself, but if you just go further, then it starts getting more obvious what the task parallel model buys you. So suppose I want to process all the files in a directory with some function called process that returns an integer, and then I want to sum all the returned results and return that. So the way I can do this is I start by first calling this activity list files. It returns me a list of files after a while. This could take a while. I don't know how long it takes. Then I call in for each of these returned ones. So this is link semantics, which basically just means I'm taking this list and I'm applying this function to each one, which is invoking this second task, which returns a list. So, and then I wait on all the tasks in that list. So that's this step here. And then there's a final step where I take all the results and sum them up. So you can see it takes me like 4 lines of code to express this diagram. And some things are sort of important here in the sense that the list and, the number of tasks run and the arguments, all of this is dynamic. So it's really the execution of this first task which determines what is going to happen next. So these are not static task graphs. They really develop as they execute. Now, an important guarantee we make is that we do give you reliable execution. So how does that work? So the idea is actually pretty simple. So what we do is we persist the history of events. So for example, say we have, similar to what I showed on the previous slide, we have a task A followed by 4 parallel tasks B1 to B4. So a typical execution could look like this. I record in the history that I started O, and I record that I started A. Then at some point A returns and I record the result, which in this case, say, was 4 file names. Then I'll start the 4 tasks that are called with these 4. There's a typo here, this should be F2. And so then I wait again. At some point, these tasks complete. Of course, they don't complete in order because they may have, different sizes and whatnot. So suppose B2 returns first, then B4, B1, finally B0. And because this was the last one, now the whole orchestration can complete with the final result, which is the sum of all of those numbers. So the fact that we persist this as a history of events has several advantages. So for example, users can actually look at this in storage, and this is helpful for them to know what the application is doing, which is one of the original problems of serverless applications, is that users need a way to understand the state of their application. But another interesting thing here is that I can rehydrate the state of these orchestrations from a prefix of this history. This is important to handle crashes, but it's also important to do that if I have long-running workflows that have long periods of inactivity. So then I can they just live in storage. They don't consume any memory. And when it's time to proceed, I can resume them. So you can see here, I marked these red lines. These are episodes. And what that means is that this actually executes as steps that are each functions. And this is somewhat important from a billing perspective. So when you get charged per invocation, what it means is that you really get charged per batch of steps that is executing. And as you can see here, I processed 2 of the task completions in a single step. It doesn't seem like a big deal here, but if you have thousands of these tasks, then of course it's nicer if you can batch process the results. Now, what about the recovery from partial histories? So here's an example of a partial history on the left where A has started and completed, check mark. And then I have started 4 tasks, and of those 4, 2 have completed, but 2 are still running. And say my system crashes at this point. Now, I have recorded this intermediate state in form of this history. How do I recover from that? So the way we do this, and there can be other ways to do this, but what we do now is we replay the orchestration. So here is the code for the orchestration again. So what we do is we take this code and we take the history and we start executing from the beginning, but we are not actually going to do anything in terms of activities calling tasks until we reach the end of the replay. So for example, if I hit this during replay, the first thing I do is this first line. I'll call list files, but I won't actually execute it. I will create a placeholder. And that's a good thing because the very next thing here is that it actually tells me the thing returns and it gives me the result. So then I just use that result directly instead of calling that task. So then similarly, it continues here. So I create placeholders for all of these. And then my replay gives me the 2 of these tasks already complete. So at the end of the replay, what I end up with is with 2 placeholders that haven't completed. And now I restart those. So basically that brings me back to the state I was in, where I have A, B2, and B4 completed, and B1 and B3 have now been restarted. So there's 2 important problems, or like things that aren't as nice as we would like them to be with this replay. And one of them is the determinism of the orchestrators. So if programmers write orchestrations that are non-deterministic, then the replay diverges, and there's no real saving from that. So if that happens, we basically have to throw up our hands, and programmers have to figure out what happened and how they will fix it. Another issue is the fact that we restart activities, of course, could be observable. So if an activity crashes after it did its work, but before it persisted its result in the history, users will actually notice that it executes twice. An activity could, for example, have an external effect, like sending an email or making any service call. So you could definitely see a duplicate of that happening, and that's a common problem in these composition of services scenarios. So it's not just our problem, it's actually a common problem. So it's really with the user, the responsibility remains with the user to correctly separate the deterministic coordination from the non-deterministic work. And I think there is some research opportunity there to maybe do better. So how do we do this today? Well, we document common pitfalls. So those would be typically time of day, random generators, I/O. If you read some arbitrary file, it's obviously not deterministic. Global static variables could be one of them also. So it's not that you're not allowed to do this, but you just have to either use our built-in versions that are deterministic, or you have to wrap them in activities to record the result. We also have a static analysis tool that will help find some of these errors. And there are some other ideas. So one great way to handle this would be a language with an effect system that can type check for non-determinism. So Dan Lyon has one of those. We have tried this, it does work. There's also the option of trying to automatically wrap request handlers in JavaScript. So I did work with Christopher on some level of automation for this. It wasn't fully automatic, but it was easy to create the wrappers. Okay, so that was about orchestrations. Now, the other topic here is entities. And so this is another construction that is useful to write stateful, to bring state into a serverless context. So this is more similar to actors, and particular virtual actors. The idea here is that I represent application state as a finely partitioned storage key value pairs, or maybe key object pairs, because the value actually has operations that can be executed on it. And the important guarantees are that messages to those actors, or we call them entities, have exactly once guarantees for delivery. They have ordered delivery, and more importantly, they execute one at a time. So this gives you, this is an example of the synchronization guarantees that people struggle with in the serverless context. So you saw earlier an example of a serverless function that reads from storage, increments by one, and writes it back, which is not safe in a concurrent invocation. So with an entity, you get the benefit of a scheduler that executes one operation at a time. So those things now become safe. And that already is quite helpful. So here's an example. I can represent a bank account by having using a class type of syntax. I define an interface. It has two operations, get and modify. And then in the implementation, I give it a state. This will be saved to storage. And I have two operations, and I am guaranteed that those execute atomically. It's basically a monitor. Like, it's almost embarrassing because all the things I'm proposing here are super old. You will see more examples of these, like really old things that I'm, presenting as the holy grail of programming. So an interesting thing here that is not just that the same old monitor is that this still is a distributed system, even though if you don't really quite see it. So what that means is you can think about some things like one-way versus two-way communication. So we allow, for example, that an entity can signal another entity, which is sending a message without waiting for any result. And often it's better actually if you have a workflow, for example, you don't want to do the signal thing because you're not seeing any exceptions, you're not getting any acknowledgements, you have ordering issues. So more often than not, in an orchestration, you actually want to use a call response pattern where you're waiting for the result of the operation or just for the completion acknowledgement. One important thing that we do is we have some restrictions in the model. So we don't allow an entity to call another entity. And this is to prevent deadlocks. So And that's a difference from the virtual actors in Orleans, which can deadlock. Deadlocks do resolve there using timeouts, but that requires putting timeouts into the system. So for us, we actually prevent the deadlocks simply by having restrictions on the programming model. Are there any questions so far? I think we have not asked for any questions so far. It's kind of bad practice. Is everybody still here? I'm sure you're all like trying to find the unmute button and can't find it. That must be the only reason why I'm not hearing any responses.
Yes, I'm here.
Okay. Oh, good. I heard a response. Thank you. Okay. Any questions? No. Okay. So one thing that I think is interesting here also is, so we have these two concepts of orchestrations and entities. You can sort of trace them back a bit. So orchestrations were part of durable functions initially. Entities are really modeled after Orleans, the virtual actors, but they're a little different. And there is some synergy between those. So there is this, as I mentioned earlier, we have now the opportunity to do something that was not possible before, which is critical sections. And of course, I'm kidding here because this is like the most basic synchronization primitive that people use when they program on a single machine. But it's also not one that you get in a distributed system usually for a very simple reason. It's because of the failures. So critical sections don't really work if someone has a lock and fails. So that's really why they're not commonly used. And the advantage that we have is that orchestrations are recoverable. So even if you fail, like you have a crash while holding a lock, it will be recovered and it will release the lock. So that's why we can make this work. And of course, critical sections, we know they work because we have built so many things using them. So one thing that often comes up is transactions as a comparison. And so we do believe transactions have a role to play in this story, which we haven't quite done yet. But there's also something that is nice about the critical sections, which is that they don't require a failure handling explanation. So the ability to roll back effects. Transactions are built on this idea that you can roll back an effect. And that works great if you're in control of the state. But for the systems you're building here, typically there's a lot of state that we cannot roll back. If your activity sent an email, you can't roll that back. So it is arguably, it may be better for understanding the state that your system is in to not model such things as rollback, but as failure handling. So if something goes wrong and you have to write failure handling code, it might be easier for understanding what's happening and for debugging the system and for having a trace of what happened if you actually have explicit failure handling as opposed to an implicit rollback. Anyway, so here's an example for critical sections. Classic example, I want to transfer money from one account to another one. So I'm creating two entity IDs. I lock them. I have to declare them in advance. And then I create this proxy. This is just an object that I can treat as if it were the thing. I call the current value to get the current balance. And if the amount is sufficiently small compared to the balance, then I can, in parallel, I modify the account. So this is very standard. But it's not so standard in the sense that what actually happens is you have a protocol, a distributed protocol being generated from this code. So the locking actually means that you have messages that go around to gather all the locks, and they will lock them in order, meaning that we have a fixed global order on how the locks need to be acquired. And then when you read the balance, that is a message with response. And then here is the parallel call to modify the two accounts. And then in the end, when you exit the critical section, the lock is released. And we have a bunch of extra rules necessary to avoid the deadlocks. So you cannot nest the critical section is one of the important rules here. And there are some other rules inside the critical section, which I won't go into detail, but the choice we made here is to rather have runtime exceptions if your code, violates some locking rules than deadlocks, because deadlocks are pretty bad here. You can't really escape them. You can't restart your program because everything is persisted. So once you're deadlocked, you're actually stuck. So we don't want that to happen. So durable functions have been out for about 2 years, and they're pretty popular. So we get more users all the time. They're also popular compared to just stateless functions. So we have maybe 50% of people who use the Microsoft stateless functions, which are called Azure functions, also use durable functions. So the entities and critical sections are pretty new. We shipped that last year. And there's a lot of work that we still want to do. So I think I'm going to hand this back to Konstantinos for more descriptions on the more researchy parts that we're working on right now. So let me see if I can find my Zoom thing.
Hi again. Can you see my screen?
Yeah.
Great. So, yeah, I will talk a little bit about the work that we're doing now and about the execution engine that is underneath this programming model that Sebastian was describing. So, first of all, the abstract semantics of, we model this execution engine with the following abstract semantics. There are two computation units, stateless tasks that correspond to serverless stateless functions, and stateful instances, which correspond to orchestrations and entities. And communication between them happens through messages, and their state is modeled as an event history. So essentially, there are three transitions to this transition system. So clients can send messages into the system that can either invoke stateless tasks or can be sent to some instance which, given its initial history and a sequence of messages, produces a new history and maybe new messages to go to clients and new tasks and other instances. So the implementation of this engine is distributed in the sense that there are multiple partitions, each of which handles a different subset of instances. They are reliable, so they guarantee exactly once execution for everything internal and at least once for external effects. And this happens because everything is persisted, and persistence happens incrementally. So there is no stop the world snapshot that happens every now and then to persist the whole state of the system. So persistence happens using these input queues and these logs. And it's also elastic in the sense that if we have more load, a new partition can be spawned to handle this additional load. And then if the load is reduced again, it can be stopped. So the main source of overhead with this implementation are the storage accesses, which at the moment are pretty fine-grained and happen very often, and network communication. So at the moment, we're working on some optimizations to resolve these issues. So first of all, we are working on a speculative message exchange, where essentially partitions are able to exchange messages between them before their dependencies are persisted on the logs, allowing for faster progress when there's a lot of communication between partitions. And to do that right, we have designed a recovery mechanism that guarantees that there will be a causally consistent recovery if partitions crash. And another optimization is that messages that have the same source and destination partition, they are now processed in memory without being first persisted to the input queue of that partition. And we're also doing some message batching when accessing storage and sending things over the network to improve overheads. And tying all of this up, we're working on a proof of correctness for all of this, and hopefully we will submit this work soon somewhere. Yeah. So let me pass this to David now.
All right, let's try it out. Okay, I'm the host now. Just 1 second. Share. Okay, I take it you all can see my screen and that you all can hear me well. If that's not the case, this is the time. Okay, great. So yeah, before moving forward with a demo, I wanted to take you all on a quick tour around the programming experience that we've built around durable functions. This being the case because in addition to the research effort, durable functions is an offering that programmers already use today to build serverless stateful applications. And so we're trying to design an experience around it that's delightful. And we're personally really excited about it. And I want to get you all excited about it by hitting on some of the main ideas. So if I can, yeah. So there's three main goals we've been trying to achieve with some of the tooling around durable functions. The first one being the prevention of common errors via live code analysis, especially because getting used to a new programming model, especially if you're a beginner, if this is the first time you're dealing with something like this, can be difficult, and we're trying to minimize some of the pain points around that. Number two, we want to make it easy to leverage common usage patterns, which we think highlight some of the strengths of durable functions by providing ways of quickly putting together solutions, and we'll talk about those soon. And finally, as we've hinted at before, we want to make it easy to bring the language ecosystem that you're already familiar with. So we want people to be able to use their preferred language of choice. So I want to tackle these one by one, starting with preventing common errors. So as Sebastian mentioned, we have these code constraints, these caveats, right? One of the big ones being around what is allowed to be, what has to be deterministic and what is allowed to be non-deterministic code. And the bird's eye view summary is that orchestrators, in order to remain replay safe, and for other reasons, need to be deterministic and deal with deterministic code. And so we encapsulate non-deterministic computations, or the real work, if you will, around these activities, which yield back the results back to the orchestrator, and thus maintain this separation of concerns. But the truth is that, we as programmers, this is a subtle difference. We're likely to get this wrong, especially as we're just beginning to internalize this programming framework. So instead of, as we hinted at before, instead of just throwing our hands up in the air and saying, well, it's your responsibility, we're providing this coding companion, if you will, for C# developers. It's just a live code analyzer. And what it does is as you're coding your solution, it's checking for these constraint violations, things that you may not necessarily think of as non-deterministic, that you may be sprinkling in your orchestrators or whatnot. Things like random number generation, reading environment variables, checking the time, or even just using the API incorrectly, right? We have a Rosling code analyzer, Rosling being, of course, this framework for writing code analysis tools for .NET. And in the presence of these errors, we're trying to provide programmers with feedback around using the replay safe APIs and other kinds of refactorings that they may want to consider in using the framework correctly. So the idea here being, recognizing that this is a framework that requires some getting used to, especially because of the code constraints, and we want to make it as easy as possible for folks to be productive with it as soon as possible. And on that same vein, we also want folks to get straight to their business logic and not have to deal with the boilerplate around necessarily setting up orchestrations, entities, so on and so forth, or the common patterns. And so what we've done here is to identify a series of usage scenarios that highlight some of the strengths of durable functions. This includes things we've talked about before, such as parallelizing work via fan-out, fan-in pattern, monitoring long-running workflows, or designing human-in-the-loop computations, which would normally be quite difficult to do without this kind of framework. And so this and more form part of a collection of patterns that we informally call the durable functions common usage patterns. And users are able to easily incorporate samples of these and templates into their IDEs via plugins. Sorry, the slides acted up. Via plugins such that they can just fill in the blanks and change whatever needs to be different for their own use case. Finally, we believe that this is a reusable solution, as we said before, which is why we provide several front ends. We try to embed this programming framework in an idiomatic way for your language of choice, for whatever you're most comfortable with, for whatever is right for your project. And so, of course, we have some language SDKs, some front ends already supported for .NET, JavaScript, and TypeScript. But we have larger ambitions than that. Extremely soon, perhaps frustratingly soon, because I wish I could say it's now. We're about to release some language SDKs for Python and PowerShell, really anytime now, which have been highly requested by our users. And just in general, there's an ongoing conversation around making it easier for third-party folks to incorporate the model into their own languages. I kind of challenge any of you to make a Haskell SDK. That would make me happy. But overall, we're just trying to build an easy experience for people to get started with the framework. And hopefully some of these comes out in the demo. So I'm gonna let you take it away, Sebastian. Let me just share the host with you. Here, more, make host. Yes. Take it away.
Great. Thanks. Can you hear me? Yeah, great. Okay, so I have, for the remaining time, I wanted to show you the demo. So there's not a lot of time left, so I have to focus so I don't get lost. So the way I'm going to do this is by showing you the process in Visual Studio Code. You see my screen? Yep. So we are in Visual Studio Code. This is the opening window. I have nothing already prepared. I will not type everything, but let's just pretend I do. So how do we start? Well, we start by going to this little plugin for Azure. And in there, I will find that there is a button called Create New Functions Project. So it's right here, Create New Project. And it's going to start by asking me for a folder where I want to put this. So let's create a new folder called Demo. And I'll use that. Language. So C# is what I'm doing here. And it asks me for a template for the function. You can see there's a lot of different types of functions with triggers. What I want is the durable functions orchestration. And I'm going to call this transfer because this is a function that transfers money between accounts. I'm going to leave the namespace default. And I'm going to use the local storage emulator. Okay, so you can see the thing is starting to create the files that just get me started. And then it's going to open it. So I start with a project ready. You see on the left here, these are the files that are already there. There are some basic files for settings and things like that. One thing I want to actually change pretty much right away is I want to use a slightly newer version of the runtime. So let me make this 2.2. Quick change. It also created this file called transfer. And this is a template for 3 functions that together, implement an orchestration, just like the samples we showed you earlier. So there is a function that is the public surface where an HTTP call comes in. It will call an orchestration example here, which does 3 sequential calls to activities which are here. Now, we're going to modify this for our example. So we don't want any of these contents here. We don't want to return anything here. We want to, this name is good, transfer. Actually, let's call this transfer orchestration. We don't need any activity for this example, so let's just delete that part. Then transfer HTTP start, we want to just call that transfer. So this is the entry point for the REST call. And the verb here that we want is post, since it has a side effect. So let's remove the get. And there's another little change I want to make. I want to use a HTTP request, not request message. And here I want to return the I action result. So all these little changes that I'm making are just little things that get in the way sometimes. But here is where I get called, and I also want to replace this. So what do I do when I get a call? I get a web request, a post request. So I want to first extract the parameters. So what do I do? Well, I say, let's get my input from the body of the HTTP request. You can see I have little squiggles here. This is probably because I need to include some library. Yep, that was it. Looks like I need to also include something here. So here I get the input, and then I want to start a new orchestration. So what I'm going to do is I'm going to say starter. Let's call this client. Starter is a strange name. So client, I want to start a new orchestration. So this is called start new async. I have to give it the name. So the name that we had was called transfer orchestration. I have to give it an idea, which it should auto assign, and the input. So here's where I'm passing the input. And then the result of this is going to be an ID, which I'm saving. And maybe I should just return some text message like so that I can tell what was happening. So I'm starting the orchestration with this idea. Okay. So this much code should get me through creating, there's another package here. So this code will handle the incoming HTTP request and start an orchestration with the input that came in. So then the runtime will start that orchestration here. So it will run this code. with a context object. The context object is what gives me access to orchestration, context things. So what I would want to do typically is first I would want to get all the input out of there. So I'm not going to type all this. So let's just say I typed very fast. So here's the input. I'm taking it out of the context as a string. I'm creating this into a Java JSON object. And I'm reading the 3 parameters that I want, from, to, and amount. Okay, so we're starting to get done with the boilerplate. Now the interesting part. So, but you know what? Actually, before I do this, let me just check that this is actually working. So sometimes it's good to check the boilerplate. So let me put a breakpoint here and actually compile this. Oh, I see. It looks like I have to restore some packages, but that should happen. So when I run this, I hit F5 and I'm running this. What it means is I'm running this locally on my machine. So I'm not actually in the cloud yet. This will be a later step. Okay, I probably made some mistakes here. No, this is fine. That's a warning. Oh, and you can see here that this nice little pixel art, it's not pixel art, it's ASCII art or whatever you call it. That means that the functions runtime has started and it's executing. It's starting up actually. And it will tell me here what are the endpoints on which it's listening. So you can see that the method that I wrote is here. It's being listened on. And maybe I want to actually try this out. So I will create a little terminal here. Let me run a normal shell. And I'll try to curl this with some input. So let's say something like maybe this. So you can see I'm giving it some input here, which is 3 arguments, and I'm calling the local endpoint. And here's my breakpoint. And you can see if I'm hovering here, yes, I got all the arguments. Okay, so the baseline is working for just getting the thing running locally. So we're out of time. Well, I'll keep going. Does anybody have a hard stop? If anybody has a question they would like to ask right now before we continue the demo, feel free to interrupt. I think I would be able to see any hand raising if that is happening. But
I'm also monitoring the chat. So
okay, good.
I'll see it.
Thanks. All right. So in the absence of any reactions, I will assume everybody is fascinated and I'll keep going. Okay, so I got this working to this point, but now I need to add some real code. So first, let's stop this. Close this. Oh, well. Okay, okay, so let's remove the breakpoint. So what was the real code I wanted to add here? Well, it was the stuff from the slides, right? Here's the slide. So this was the critical section I had talked about earlier. So let's put that in here. And probably format this a bit. Okay, so is this, well, what's happening here? Okay, so I have a little bit of syntax that I have to fix. Context is called context. Amount is called amount. And of course, I haven't defined my account entity. So I have to define that as well. But other than that, this seems to be passing here. So let's define the account entity. So I'll go back over here. I create a new file called account.cs. I will probably go ahead and just copy this whole header part into over here. Okay, to get this. Now I need the code for the account entity. And again, we actually had it on the slides. So I'll go to the slides. I need the interface. So this is the interface for the account. And I need the implementation. Okay. So this seems to be all I need to define the account. And I think at this point, we would be ready to run this, except there's one thing, which is if I run this, then it's actually not going to be easy to see what's happening because I can't read the current state of the accounts. So I do want to add something that lets me read the state of the account. And so let me add another thing here called list all. And this one, I'm probably just going to drop in here from my off-screen text editor here. So here's another one. It just lists all the entities in the system and, you know, returns what the current balance is. Okay, almost there. One last thing. When this starts, the balance in the account is initially 0. So let me just make this 10. It makes it a bit easier to give this demo because if I want to transfer money but nobody has any, it's not going to work. So if I just put some default money into each account, it should work. Okay, so let's try to run this locally. Okay, thing is still starting up. It's doing a lot of things. Okay, you see we have 2 functions now. We have a list all endpoint and a transfer. So let's try the list all. And it returns an empty list. So this is to be expected because we haven't created any entities. The cool part about entities is that by default, when you call them, they get created as you call them, just like virtual actors in Orleans. So we can just transfer. So let me just run a transfer from a map from, okay. Oh, okay, never mind. So what happened here is I called curl from the Windows shell, which wasn't happy with my syntax. So let's get out of here. All right, do the same thing. That's better. So you can see I got a message immediately telling me that the orchestration was started, but it still kept going because this just meant it was started, didn't mean it completed. But now it actually completed. So now if I do the list all, I should actually get the result that I expect, which is, yes, so I have 2 accounts now. Both of them had 10 initially. So after the transfer, A has 0 and B has 20. Yeah. So my local demo worked, but like, why are we doing all this? Well, we want to run this in the cloud, right? So we have to do that part. Now, it's actually not as hard as you might think. So how do I get this to the cloud? Well, let me go back to this magic Azure panel here. Here's this button here, deploy to function app. That's what I need. It looks like I have to sign in. I already did this many times today, but of course it you know, have to refresh the tokens and whatnot. Okay, that seems to be working. So I need a script subscription, so I'm going to go with revision service. And I need to create a function app. So let's call this PLDI Tuesday demo. Oh, cancel. This is not what I wanted. It auto-completed me. Okay, try this again. Why does it override? Okay. I just need a different name, so I can do that. So where is it?
It's at the top. It was the first option.
Oh, okay. Yeah, thanks. Okay. That'll do it.
Maybe you have to click create new. There was like the second option.
Oh, thank you. Okay. Yes. Sorry, could have done that better. Okay. So that was the whole problem. Okay, where should I start this? Any votes? Who is like the most remote from us? Nobody's here. Okay, let's just do this in, I don't know. Okay.
Remote Canada.
Remote Canada? I've never tried this. Okay, if everything goes wrong, then it's because of that, not because of any other reason. All right, so you see at the bottom right, it's creating several things. So the function apps include storage accounts, and they can include the function apps, and they include, you know, app services, and they include monitoring component called application insights. And so this actually isn't that fast. So, you know, it's progressing. It's step 4 or 5. That's good. But step 5 or 5, okay. But it does take a moment to create all these resources. You don't have to read, like when you redeploy, you don't have to do this every time. It's just the first time. And the other thing is, at some point, it does make sense to actually go into Azure and watch your deployment in this portal, because you get a whole other range of options when it comes to monitoring. So, for example, it doesn't look like it's here yet, but it will show up here at some point. So you get a lot of options for monitoring in here. Let's see how it's doing over here. Yeah, it's step 5 of, oh, okay. Maybe it's doing something. It's publishing. Let's see if we can see it on here. No. There it is, PLDI2 state demo. So you can see I get some information about this. It's in Canada Central, like we asked. It does what we asked it to do, even if that doesn't make any sense. And now we have some functions that we can look at here, I guess. They're not here yet. So let's see what the status is. Okay, so it's still deploying. Completed, that's good. So that means we should see them here. Let's refresh. Not quite. Yeah, here they are. So you can see I got my functions, which are the account, the list all, and the transfer, and the transfer orchestration. So that means we're officially very close to trying this out. So let's just have a quick look at the example of this function. So you can go here and you can click this and you get the function URL. So this is usually how I get the URL, but you can also just know what it's going to be. So let's get to the final step here, which is to test this demo. So I'm going back here, creating this. Let's make this a little bigger. And let's not forget to use bash instead of the Windows shell. Okay, so now the moment of truth. So I'm trying to list. This is now starting up the function app. It took a moment because it's, maybe you have heard of cold start, so it had to warm up for a moment, but it worked. I got an empty list. That's just as for the local test. And now I'm gonna do the transfer, just like on the local test. And it did seem to do something. So the final test is to check if the results are as expected. Yep, worked. Okay, demo is complete. Great, thanks. All right, so yeah, so now we wrote a bank, and in a future version of the demo, I would now start some load generator and show you how it scales up and down depending on load. But not today. I think we're done for today. So do we have any audience questions? Okay. So it is quiet. And thank you all for watching this. I hope
Thanks,
you were
folks.
not bored to tears. But yeah, it's not, you know, this online thing, it's not quite like being in the same room, but I was happy to actually still be able to do this. So thank you for coming. All right.
Thanks, folks.
Thanks, guys.
Find us on GitHub.
Yep. I put this back into my other place.
I have a question.
Okay.
Took me some time to find the unmute button.
Yeah, it is difficult sometimes. Yeah.
So during your presentation, your section of the presentation, you were saying that if I understood correctly, I probably missed something very obvious, but I felt like you were checkpointing intermediate results. So you had like file 1, 2, 3, 4 at some point.
Yeah.
Is this so? Wouldn't this cause like a crazy explosion in terms of intermediate results, or how does?
Yes, so there's two things that are important to not have a crazy amount of intermediate results. So one is the granularity of the tasks needs to be relatively large. So you wouldn't want to take an existing program, you know, that makes millions of function calls per second and try to treat it like a task parallel program and persist every little piece of it. That's not going to work. What we're looking at is a modest number of tasks that are pretty coarse-grained. This is the same, by the way, if you do task parallel programming for just general parallel programming. You need to it really starts working much better if your tasks are not too small. So that's one part. And then the other part is that there is some amount of batching going on. So especially with the more optimized implementation we have underway. So we'll actually be able to have much fewer storage accesses than number of steps in the workflow, because we can batch the storage accesses.
Mm-hmm.
So those are two important things I think to keep in mind. Yeah.
Thank you. Thank you very much. Great presentation, everyone.
Thanks.